Hey, Calculus. This video is a short review over everything we saw today on continuity of functions. Compare your notes to mine if you have them close by, and let's go ahead and get started here. So, in order for us to show that a function is continuous, we need to meet three conditions. The first one being that we need to know that if we plug a value into our function, let's say that value is a, some constant value a, we need to know that the function is defined at that value, okay? So if we plug in a value for a, we get the function's definition of that value out, okay? So that point a, f of a exists. The second one is that we need to know that the limit as x approaches that value a of our function, whatever it may be, whether it's a singular function, a piecewise function, trig function, exponential function, we need to know that that limit exists. Okay, and remember, the way we prove that a limit exists is that the limit as x approaches a from the left of our function is equal to the limit as x approaches that value a from the right of our function, whatever it may be. Okay, f of x. All right, and the third one is that the limit that we tested above as x approaches a of our function is equal to the first value we tested. Okay, and remember, there's a way to prove that. It's a process. Okay, so as soon as one does not check out, we know it's not continuous. All right, so let's try a function out here. Okay, let's say we have the piecewise function f of x equals the following here. Let's say we have x squared plus 4 for all of the x's less than 0. And then let's say we have 2x plus 4 for all my values that are greater than or equal to 0. Okay? So without even graphing it, here's how we can use the process from before. First of all, we need to test, and we're going to test the point x equals 0. See if it's continuous at that value. Okay, so the first thing we're going to do is, of course, test f of 0. Okay, and in this case, we're going to use 2x plus 4 because that's where it's defined for the function here. So that means I'm going to have 2 times 0 plus 4. So in this case, 2 times 0 is 0, 0 plus 4 is 4. Okay, that's a definitive value, so we know the point 0, 4 exists here. All right, and then we go to the second one. We have to prove that the limit as x approaches 0 of our function exists. Okay, so once again, we have to test it based on the left-hand and right-hand function. And the way we do that is, of course, because of our limit laws, we can just replace 0 in all of our functions. We have to do it from the right function, though. So if we test x squared plus 4, because that's everything to the left of 0, because it's all of my values that are negative, that means I'm going to do this for my left-hand value, x squared plus 4. That means I'm going to have 0 squared plus 4. 0 squared is 0. 0 plus 4 is 4. Okay, so that checks out so far. Let's do the same thing for the right side. So limit as x approaches 0 from the right. Now it's a different function. It's 2x plus 4. Well, let's see. So 2x plus 4, that means, just like we saw in the first part of this, that means that we get 2 times 0 plus 4. And we saw from the previous problem that we have 4 there. Okay, so we have that much. We know that this is going to be 4. That exists. And then the last part is we compare the answer we got for number 1 and number 2 and make sure they agree. So does f of 0 equal the limit as x approaches 0 of f of x? And in this case, it definitely does. We got 4 for the first part, and we got 4 here. That means that we are definitely continuous at this value, x equals 0. Okay? One last thing I wanted to show you is the types of discontinuity that we run into and what their conditions are. All right? So the first type that we have that I'm going to draw here, once again, you can just compare your notes here, is, I'm sorry, let me switch my page here. The first type of discontinuity that we have is a removable, and that's just basically if we have a line, all of a sudden there's a point here, and it keeps going like that. That's an example of a removable discontinuity. Okay. Now remember, just like I said in class today, even if we do have a defined value for it, okay, so let's say it's above the line here, that means that it's still removable because we need to know that, there's not a hole in our graph here. So the way we prove, once again, just like we saw before in class, the way we prove that we have a removable discontinuity is that the limit as x approaches a of our function exists. Okay, so if this is my a value right here, as we approach it from the left and the right side, then we know that discontinuity exists. Okay, the second type of discontinuity that we have is, like we saw in class today, is our jump. I'm going to put this in orange. I feel like being different. Is a jump discontinuity. Okay, the way that works is, let's say we have a function that looks like this. Say we have kind of a parabolic shape here. We have a point here, and then our function continues like this. Okay, and the way we prove that a jump discontinuity exists is that if we know that the limit as x approaches a from the left exists, and that the limit as x approaches a from the right exists, but our general limit as x approaches a of our function does not exist. Okay, so if this is my value a right here, we can see that coming from the left, as we get closer and closer to that a value, we know that this limit exists. Same thing if we come from the right and kind of follow this along here, that limit exists, but they're not the same value. Okay, and then last but not least, the third type of discontinuity we're going to run into while we're doing our work here is going to definitely be our infinite sort of discontinuity. And this one's a little bit more intuitive in the sense of, if we have a vertical asymptote, so for instance, if I have a vertical asymptote right here, and we'll call this my a value, and I have kind of a rational function like this, then I know that that has to be an infinite discontinuity. Okay, and here's how we prove this. So an infinite discontinuity exists if, when we take the limit as x approaches a of my function is equal to either positive or negative infinity, and the same thing, I forgot to mention that's from the left, and then if the limit as x approaches a from the right of whatever function we're looking at is equal to also positive or negative infinity. Okay, so I hope this was helpful. Once again, compare your notes to mine. If this was helpful, drop a like on this video. It helps me out. It makes me feel like, I'm actually being watched. So have a good weekend, and we'll see you guys on Tuesday.